And right now we have Christina Psaroudaki, and she's going to be talking about skyrmion and frustrated magnons. Actually, skyrmion helicity in frustrated magnons. And take it away.
Thank you for the introduction and for inviting me. It's my pleasure to be here, of course. So we are located at the heart of Paris, but our building is not so beautiful as you can see here. So I included a few of other things that you can reach within walking vicinity to convince you that we are working in a very beautiful place. So this talk is about magnetic skyrmions, which is a very beautiful application of topology in condensed matter. And these are these texture quasi-particles like the one you can see here, where the spins at the center of skyrmion point in an opposite direction than the ones in the ferromagnetic background. And there is one straightforward way to classify them and found their topology, where we go from a mapping from real space of all the spins into the spin space. So all the spins in the ferromagnetic background, they compactified and they're mapped into the point here. And all the other spins, they also are mapped in the spin space. And then we measure how many times the magnetization wraps the unit sphere. So in this example, we go from up to down once. So the topological charge is 1. If we do the same for the ferromagnetic state where all the spins point up, of course here we just have a charge that is 0, and this state is separated by the skyrmionic state by an infinite barrier in the ideal case. So that's the concept of topological protection. Once we realize a magnetic skyrmion, it's very hard to destroy it. Of course, that's a concept that exists only in theory. In a real material, we have defects and other deformations that lower this energy barrier, but still skyrmions are quasi-particles that have relatively long lifetimes. The topological number that will appear several times in this talk is calculated by a formula that is given here, where M stands for the magnetization texture, the magnetization field. So originally, skyrmions were observed in a skyrmion lattice, as you can see here, in certain materials at relatively low temperatures, in a particular pocket of the phase diagram in terms of magnetic field and temperature. Of course, once we increase a bit the magnetic field, we destroy the skyrmion lattice, and we can only realize a few isolated skyrmions here and there. They have been studied with a lot of probes, including electrons like Lorentz TEM, scanning probes like MFM or NV, photons. The X-rays have the right wavelength, and scattering techniques. And they have a lot of interesting properties that I will not summarize, because this is not a talk about skyrmions only. But they have a very small size, and they're very mobile. They have a lot of control properties that will allow for compact and low energy consumption devices. And all those properties gave rise to the emergent field of skyrmionics, which is already relatively large within the spintronic community. Now, where do we realize, or what kind of models do we need, what kind of materials do we need to realize magnetic skyrmions? We would need interactions that are competing with each other. So on top of the Heisenberg model, between a ferromagnetic Heisenberg term between nearest neighbors, we would need a term that tends, for example, the spins to align in this direction, and that is given by the famous Dialonczewski-Morillet interaction, which arises from spin-orbit coupling. This Hamiltonian has a very rich phase diagram, including a cone and a helicoid as ground state, the skyrmion lattice that I mentioned before, and we will be focusing on isolated skyrmions that exist above the ferromagnetic background. Now, for this term to arise, this Dialonczewski-Morillet interaction, we need to break inversion symmetry. There are several materials that lack inversion symmetry in the bulk. I give here a few examples of those materials. They're very well studied, and skyrmions in those materials are also very well studied. But inversion symmetry can be broken also on the interface between a non-magnetic material and the magnetic skyrmion hosting material. And there is also a lot of work in this direction. Now there is an emergent material category which is based on frustration. and the model is the one that I give here. So we have ferromagnetic between nearest neighbors and antiferromagnetic between next nearest neighbors. This is also competing interactions between those two. We can also have the magnetic field and some anisotropy. And this model has been studied quite recently, and we also know that this model supports skyrmion lattice phase and isolated skyrmions as in the phase space phase diagram. And in 2019, there is a number of materials that belong in the rare earth intermetallics where skyrmion lattices have been observed in this material category. Now, I'm focusing on that, and I give an emphasis on this novel material category based on frustration, because the skyrmions that we realize there are much smaller in size. So if we're interested for quantum effects, they're most probable to have a quantum behavior. And there is a new degree of freedom that I will call helicity, and I will explain shortly, that gives rise to novel, non-trivial magnetization dynamics. So in this example, we see plenty of skyrmions. All of them have the same topological charge. So in all cases, the spin goes from up to down, but they have a difference in how the spins swirl as we go from up to down. So the way we characterize this spin swirling is called skyrmion helicity. It just takes a number. And I have plotted here the most famous two examples where we have a Snell skyrmion and a Bloch skyrmion. And of course, depending on the stabilizing mechanism, we can have other types of skyrmions that we have here. Why helicity is important is a central topic of this talk. But if we stabilize skyrmions using dipole interactions, that will give rise a cosine of 2 phi naught potential. So the helicity is fixed by dipole interactions, and the resulting skyrmions are relatively large. So from 100 nanometer to 1 micron would be a typical length scale for a skyrmion. Or if we have the Alonzinski-Morilla interaction that I mentioned before, depending whether we have bulk DMI or interfacial DMI coming from the interface, we can stabilize either an L or a Bloch skyrmion. There are a few experiments where it has been, people can recover what is the particular helicity, whether we can have an L or a Bloch. And the relative length for those skyrmions are about 10 to 100 nanometers. So still large, but smaller than what we get from dipole. Now in this emergent material category based on frustration, we have a global symmetry of rotation. So there is no intrinsic potential for the helicity. All of those realizations that you see here, they carry the same energy. And also the resulting skyrmions range between 2 to 10 nanometers, so they're very, very small quasi-particles. So that's like the two key properties that we should point out here. First is that we have small skyrmions, and the second is that we have a degree of freedom, which is the helicity. So there is no potential term that helicity fills. Now, since the skyrmions are small, that motivates us to go into the quantum regime. Skyrmions have been extensively and largely explored in the classical regime for spintronic applications. But there is a motivation in some recent work whether they could have and exhibit quantum behavior. The motivation for that is that they can be realized in some magnetic materials where the skyrmion size is very small. So from 1 nanometer or 2 to 3 nanometers. And that kind of aligns, so exploring magnetization textures in the quantum regime kind of aligns with the efforts on the quantum magnonics community, where one can study magnons coupled to quantum degrees like photons and qubits. And at the same time, we are at the moment where quantum sensing techniques are being developed that have the possibility to measure quantum signals with great sensitivity, and also the emergence of similar ideas like topological magnons around skyrmion lattices. So just want to point out, it's a very timely research theme, And I would like to convince you why is that. So this is not like the first time we are studying quantum behavior for skyrmions. In an earlier work of mine, we have established, when I was working in Basel, that skyrmions are being even classical skyrmions are affected by quantum fluctuations, and quantum fluctuations can affect their motion. And we also established that the magnetic skyrmion can behave as a microscopic quantum particle. For example, we could observe the microscopic quantum tunneling. Now, a bit later, there is a concept that has been defined in the community of the notion of quantum skyrmions. So there we go on the discrete lattice of spins that have low magnetic moment, so spin 1/2. There we cannot replace spins by spin operators by macro spins. And then we should try to explore whether a magnetic skyrmion could exist, for example, that has similar signatures as a classical skyrmion, and how topology can be defined there on a discrete lattice. To give more like an intuition of how quantum effects can be studied in this regime, there is like two different approaches one can take. The one is we start from a classical or a semi-classical level. Well, we have a skyrmion that is classical, but at certain limits, and those limits are very well specified, so low temperature and low overall magnetic moment, so small skyrmion size and low magnetization, it experiences strong quantum fluctuations. In that case, we can replace studying the whole magnetization in terms of some collective coordinates depending on the symmetry. So for example, its position, the helicity, or some other collective coordinate depending on the dynamic process we want to study. And then we replace those collective coordinates with operators, all right? And then we study the quantum behavior of those operators. For example, in terms of microscopic quantum tunneling, which is a very, example that all of you have studied in a typical quantum mechanics class. The second direction, as I mentioned before, is really going down to the true quantum limit, where we have a discrete lattice. Each of those lattice sides, they carry spin 1/2. And we cannot replace the spin operator here with a macro spin. We need to solve the problem numerically. And there's a line of work where people have defined states that look like a skyrmion. There have been developed like the notion of topological charge there. And of course, those two different lines of studying quantum effects should merge at some point. But I will be focusing on the first one. Now, having a quantum degree of freedom gave me the idea that it might be related to quantum computing, where we have a quantum degree of freedom like a two-level system. And we could build something that is called a quantum computer. There are some physical systems that are naturally two-level, like photon polarization or the electronic spin. But there are some systems that are not naturally two-level, like circuit parameters, but can behave as two-level systems in certain regimes, like the superconducting flux here. So I would like to add the skyrmion helicity as a new degree of freedom, where one can encode quantum information. So we are looking for quantized states of skyrmion helicity. And of course, it's not enough to identify those two-level states. Then we should show that a few requirements are satisfied. For example, that the spectrum of those degree of freedom is enharmonic, that we have the ability to initialize and control this degree of freedom. The coherence is a major player here that we should estimate exactly. Of course, scalability and whether a set of quantum gates exist. So this is like the roadmap that I followed when I was trying to develop this idea. The first is to identify this degree of freedom, and as I said, it's going to be skyrmion helicity. The next is to check whether a few of those requirements are met in terms of coherence time, scalability, and gate operations, and of course that this degree of freedom is open for measurement. So a few readout measurements should be accessible. There are some advantages, because I guess you might be wondering why we should do that, since we have very well-developed technologies that are competing. So the major advantage is skyrmions have a microscopic size, but still smaller than circuit parameters, but larger than, for example, single spins that are very hard to realize and control. And it's based on spin degrees of freedom. There is no charge here that plays any role. And this degree of freedom is very easy to address externally. And we also have a lot of knowledge coming already from skyrmionics that could be transferable in this platform. Now, I'm going to go into specifics about how the skyrmion qubit can be constructed based on helicity. So we start typically from the theory in terms of those classical variables of magnetization, and we introduce helicity and its conjugate momentum. Here a Z is just the Z component of magnetization. And as Sylvia mentioned before, of course, here we have to take into account those quantum fluctuations. Now there is a proper, well-defined way where we go from classical variables to quantum variables, which I will not talk about it here, but if you want to know more, we can talk about later. So fun fact, it's based on techniques that have been developed by Gervais in the 75 to treat King solutions in nonlinear field theories in a completely different context. But Gervais was a professor in École Normale, and I find it very amusing that the history repeats itself in a different context. Anyway, since we identified the quantum degrees of freedom and we defined a proper way to introduce their quantization, their canonical quantization, then those should satisfy the usual commutation relations. So here is like position and momentum, but here is helicity and a Z. The eigenstates of a Z are spin states, and the eigenstates of helicity are states with a well-defined helicity. Now, if we do everything correct, we arrive to a quantum Hamiltonian that contains a quadratic term. So here is the effective mass, can be controlled by the magnetic anisotropy. This term here is controlled by the magnetic field. And typically, we don't have any potential for the helicity, as I mentioned before. Yeah.
Does this Hamiltonian come from the initial Hamiltonian you showed?
Correct.
Okay.
Yes.
Just making that transformation.
Correct. Yes.
Okay.
But as I mentioned before, there should not be any potential terms. However, in reality, there exist, or we could engineer them. For example, if we have small dipole-dipole interactions, or if we use train, we can generate a cosine of 2 phi naught, so a double well. If we apply an electric field, that is going to tune the barrier of this double well, and if we apply a field gradient, we can create a depth difference. So maybe you're seeing now where all this is going. So we have a well-defined two-well potential that correspond to two states that have distinct helicities, like in these schematics here. So we are looking for eigenstates of this Hamiltonian. In this double well example, we can identify the lowest two as being the qubit states. And to proceed, we need to satisfy two requirements. The first is high enharmonicity, so the other levels that exist, because there are many levels here, they are separated by anharmonic gaps. And that is kind of easy to be satisfied in this example because we have a lot of external parameters to tune. And the most restrictive requirement is that we need to operate at very low temperatures because thermal excitation should be suppressed, and that really limits the temperature of this qubit. Nevertheless, if we focus on these low-lying states, we can plot the universal level Lipashian diagram. So close to the degeneracy here, the two low-lying states are just superpositions of states with distinct helicities. Sorry.
How are you sure that the high levels energy are not populated? I mean the 2, 3, 4. if you calculate the projection operator of those states, can you find that it's 0 approximately?
Yes. So we for a given temperature, we can estimate how many states are populated.
What is the temperature?
To avoid that, I will give numbers later, but it's around 100 millikelvin. So low temperatures to avoid populating other states. Okay, so sorry.
So are you looking at helicity as the relevant variable because these are the softest modes, the ones that have the lowest energy excitation? Yeah. Okay, so if you were to look at amplitude modes, those are just typically very high energy.
Like breathing modes? Or yes, different.
Okay, thank you. And I just want to check, is this for a ferromagnet now? You talked about frustrated antiferromagnets quite a bit at the beginning. Or is S said the staggered magnetization?
So ferromagnetic is stronger.
Yeah.
Usually the ratio between antiferromagnetic to ferromagnetic, we take it to be 1/2. You need strong, relatively strong antiferromagnetic to have skyrmions in the first place. Yeah.
Okay, great. Thank you.
But ferromagnetic is the...
I got it.
Another question? Okay. So maybe this picture is familiar to you because it's highly inspired by the flux qubit, where we have a superconducting loop interacted by a Josephson junction, and the two low-lying states that are separated by this barrier correspond to clockwise and counterclockwise supercurrent in the loop. So conceptually, it's very close because still we have microscopic variables, but here it's in terms of spin. So since we could have a flux qubit, could we have other types of qubits? Of course, then we have the operator of a Z, so spin states, right? So if we are in a limit where this term dominates over the electric field, and let's say we forget all the other potential terms, we can still diagonalize this Hamiltonian and identify the lowest two qubit states, which physically those are magnon states. And this concept bears similarities with the charge qubit, right? It's like identical Hamiltonians, where now the Josephson junction that creates the necessary nonlinearity is given by the electric field, and those nonlinearity emerges because the magnetic states and the skyrmion helicity are conjugate to each other. So the presence of a skyrmion in this definition, in this example, is very important because skyrmion helicity gives rise to the necessary nonlinearity. Okay, so to put this work in terms of what has been going on in the field, it's actually Sotake and his collaborator that introduced the first concept of solid-state qubit based on magnetization textures back in 2018, where they had this idea to use domain walls to build qubits. And later on, the Basel group with Ji Zhu and his collaborators developed a very similar concept based on domain wall qubits. There is a concept of Meron qubits, so I think there's a lot of work going on here that is very interesting to see. So in this recent publication, which is like an initiative from the UK, and I'm not part of the authors, but I was happy to see that our proposal is actually ranked as a platform with medium level of maturity, and I think this medium comes from the fact that skyrmionics technology is really well established. So we know a lot of things about skyrmions and how to control them, and we just need to maybe concentrate on some efforts to go in the quantum regime. And I can talk about that if you want. But that's kind of a summary of what I wanted to say. I wanted to introduce why skyrmion helicity is important in these frustrated magnets and whether we could use it to build a quantum computer. I didn't talk about single qubit gates, but this is very straightforward to see. We have magnetic fields or electric field protocols, 2 qubit gates, and I put a question mark here following So's way to present. Then you can see Dennis talk, if he has time, to like talk about entangling distinct qubits using magnons. Of course, the coherence rates, we can estimate them using like a simple LLG type of estimation. Qubit readout, we have a few thoughts and experimental signatures, which is still lacking. Focusing on the question, how do we really know skyrmion helicity is quantized, right? And that kind of takes us back to early experiments on superconducting qubits, where the theory was developed, 20 years before the first signature in terms of level quantization and microscopic quantum tunneling came. And Sanchar and I have an idea of how we can have experimental signatures, and he's going to talk about it next week. If you want to know more about that, we have like a recent paper that summarizes the challenges and the concepts. And we also have a recent colloquium with these nice people, these nice collaborators, on like more general concepts. So why skyrmions can be quantum, what does it mean quantum, and we explore different notions because like we can have classical skyrmions that interact with quantum states. We can have quantum skyrmions that can have all different types of behavior like quantum nucleation or quantum annihilation, and what are the challenges to address this detection in the laboratory. Okay, if you have a question, maybe on this part. Yeah.
I have a quick question. So if you could just elaborate a little bit on the like technique or approach to understand whether the skyrmion is behaving as classical or as a quantum entity. So
how we can understand? You mean from a theory point of view?
Mentioned that the work with Shankar. Like what's the
Right. So yeah. So the way you understand whether skyrmions are classical or how fast they lose their quantumness is by estimations on microscopic quantum tunneling effects. So you have a microscopic skyrmion that sees a potential, and then there is this tunneling, and there are two measurements to be sure. The first is how much time do I need to wait until tunneling effects happen, and that shouldn't be infinity, right? Because for any. And the second is what is the temperature that I can have tunneling above the barrier, right? And that shouldn't be 0. So based on that restrictions, you can calculate how big the skyrmion can be in terms of its size and in terms of the total spin, such that I'm going to lose this quantum behavior. That's a very specific calculation, and you really see that when the skyrmion becomes classical and where it's quantum. Now Sanchar's work is trying to answer another point. So if I have a quantum skyrmion in terms of helicity being a quantum variable with discrete eigenstates, how do I see it experimentally? And I will not answer that to give you...
Right.
Have you seen entanglement formation for the system?
Between two skyrmions?
Yeah.
Between two skyrmions?
Yeah.
So that's Dennis' work, yes. And quick answer, yes.
Yeah. And how about the relaxation rate or
right.
the phasing
So
rate?
the relaxation rate is an important factor. It's the most detrimental and important factor. The way I calculated it is using Gilbert damping, because that gives rise to ohmic-like terms for like in terms of these two levels, and they are the most important terms for the coherence. One could do a more microscopic calculation and somehow falls in the discussion of last days, like how much do we know about damping and how accurate is Gilbert damping. You can start like coupling skyrmions to other degrees of freedom microscopically, like phonons, defects, and magnons, and you can make a better estimation of this number, which is something I plan to do in general.
Okay, thank you.
Okay. All right. So
one more question, Christina. Not from me.
Sorry.
So you mentioned that in your talk that the degree of frustration that you need is something 1/2. And how is this rate of frustration encoded in your V of phi potential that you propose? Or is it implicit? The parameters are a function of this anisotropy degree?
Yes, but it's going to affect the mass to some level. I'm not sure the mass is very sensitive to this ratio. The most important is that you need some level of frustration to even realize skyrmions. You need, I don't remember what is the critical number, I think 1/4 or something. Once you realize it, the only terms that enter effectively would be in the quadratic term. All the others are
independent of this
independent,
of this ratio. Okay, thanks.
Okay, so the second part, how much time? I'm all in the middle. Okay, cool. Yeah. So the next part is that in any case in this system that realizes skyrmions, there are many things that we don't know because people have started exploring frustrated magnets and skyrmions there quite recently. And one of the things that we didn't really know is how the magnons around the skyrmion behaves, and that's what I'm going to talk about now. So this is a collaboration with Christos Panagopoulos, who is an experimentalist in Singapore, and his student who is visiting the physics department of ENS at Darsh. So we started analyzing this model, again, ferromagnetic, nearest neighbors, antiferromagnetic, some magnetic field and some anisotropy. If we minimize this model, we can find for certain magnetic fields, we find the single skyrmion as this ground state, like the one you can see here. Now we see how the profile of this skyrmion is, so how the AZ changes as we go from down to up is plotted here. So this is the center of the skyrmion and how it changes as a function radial distance. So here you can see this is the red plot. That is, there's something small fluctuations that span over large distances, and we call this a tail. I'm just mentioning here because we're gonna see the effect of this tail soon. And on the dotted line is just a skyrmion in a simple chiral DMI system. So there's no tail there. The skyrmion profile just drops and vanishes. These fluctuations, of course, have been reported elsewhere, both in the discrete and in the continuum. But keep in mind that we have a skyrmion tail. Now, what do we know about magnon modes around isolated skyrmions? We have the center of the skyrmion, and we have the extended magnon continuum, but there is a local potential created by the center of the skyrmion that localizes some internal modes. And those modes live below the magnon gap, and they are plotted here as a function of the magnetic field. So we could have the most famous counterclockwise mode, which is the center, is a gyrotropic mode of the center of the skyrmion. We could have something that is elliptical, and the breathing mode, where the size of the skyrmion breathes. And all of those modes typically exist below the magnon gap. Whereas the magnon states are not really affected by the presence of the skyrmion because the wavelength of those states is much larger than the skyrmion size. So they pick up a phase, but it's really very minimal the way extended states interact with the skyrmion. Okay? This is what we know so far. Now, from these localized states, a few are important because they are magnetically active. That means that we could put AC fields to activate them. If we want to activate the clockwise rotation or the counterclockwise rotation of the mode, they have a finite in-plane magnetic moment, and they can be activated by in-plane magnetic fields. If we want to activate the breathing mode, then we put an out-of-plane field, and then we activate the breathing of the skyrmion. This has been well established theoretically and experimentally if you want to follow this few of these publications. Right? So we are focusing on these modes because they are magnetically active. That means that we can excite them. Okay, so what happens in
Christina, just one
Yeah.
quick question. So when you say the breathing mode, it's AC field perpendicular to
Yeah.
the plane where the skyrmions live.
Yes, yeah. Okay. So we want to repeat like the same calculation for frustrated systems, but the first thing we observe is that dispersion relation for the magnons that live there, that don't have this parabolic behavior, but they have a Mexican hat. So that means that the low-lying modes have a finite K and a finite wavelength. And the wavelength of those modes is comparable to the wavelength of the skyrmion, right? So the modes that live down here. So then we found a number of these localized modes, and here we plot the amplitude of the dipole moment in plane. So red dots is the amplitude of the magnetic moment for counterclockwise modes. The blue is for clockwise modes. And here we just denote the lowest lying mode. This is very close to the magnon gap. This just mode, and the third one, which has a moment which is much, much larger than anything else. So I'm going to analyze those three modes. They are all of them, of course, as I said, magnetically active. And we just want to see how they behave. I should mention that all of those localized modes, all of them live above the magnon gap. So there's nothing below the magnon gap of the extended states. So the first mode, this counterclockwise mode that lives close to the gap, we plot it here. So here is there is something missing. The Z component in real space of this mode, and here is the X component of this mode. So at the center, it's what happens at the skyrmion core. If we put some dynamics here, we're going to see the skyrmion core rotating in a counterclockwise mode. But what was like interesting to us that we have all this extended magnon lattice that we didn't really know what's going on here. So we have a lattice here where magnons become localized. Then we checked what happens to the magnon wave function, and something similar happens. So we have this superlattice of magnon modes where both the wave function and the real space representation of the modes become localized. And we would like to explain what's going on here. So this kind of superlattice of magnetic excitations, I have not I couldn't find anything in the literature. If anyone has an idea, please let me know. So we would like to analyze what's going on here on this mode. Then we just figured out we take an equal superposition of scattering states. So I go back. States that have a minimum energy. So these are extended states that have this finite wavelength. And we have 6 of them, right? As you can see here, 6 states degenerate. They have the same energy that live in the Brillouin zone. And I make an equal superposition, and then this is like what we're going to get. So these patterns emerge, very similar patterns emerge from just taking a superposition of those extended states. However, if that is in a ferromagnet, so if we didn't have a skyrmion, but if we have a skyrmion, those extended states are superimposed by the skyrmion gyrotropic mode. And then we ask the question whether like these superlattices or this skyrmion can be observed experimentally, or dynamically. So can we activate this supermode? If we start from a simple ferromagnet, we put in plane or out of plane field, we cannot reach a state where we have a superposition of those extended states, giving rise to these patterns. But if we put a skyrmion in, the skyrmion gyrotropic modes is superimposed with these extended states. And here we start with a single skyrmion, we put an in-plane magnetic field on resonance with the gyrotropic mode, and then you see the emergence of those dynamical superlattices for magnons. Okay, you don't see the skyrmion rotates because we have extracted the skyrmion to give rise to a more pronounced signal. But if we put the skyrmion on top of that, you're going to see it's rotating.
what is the direction of the effective external field for
So here it's in plane
in plane?
for the AC and out of plane for the stabilizing.
Do you know if this is a finite size effect?
No, it's
from-
not a finite
it's-
size effect.
You know it's not?
No.
So, but these modes,
There is no
they
boundary here.
propagate everywhere.
Yeah, yeah. There's no boundaries here. This is periodic.
Right, but so it's periodic on some kind of surface where the right side is equivalent to the left
Yes,
side.
yeah, yeah.
So it's a finite square, right?
What we
But if you put energy into the skyrmion, would it not propagate away in these modes?
what do you mean? If there's something radiating?
In principle, yeah. If you had a larger system, would you be able to send the energy away? Because it looks like somehow you're
Yes, but you keep excite the system.
Okay.
So you just keep generating the patterns and losing them and generating and losing them.
okay.
Yeah.
Okay.
But I just want to say it's not a boundary effect in terms of gallery modes or something like that.
No,
right?
not a
There's
boundary
nothing-
effect, but a finite.
It's
size
not
effect.
standing modes.
Okay.
Yeah. Right.
But they're sort of extended across your whole
Yes,
system. So
yeah,
if
yeah.
you made an infinite system
Yeah.
with a single skyrmion, I would expect the energy to propagate away. No.
Yes, but it's going to repeat itself. So the amplitude of those guys away from the skyrmion, so it's not like those are trapped around the skyrmion. So we see you see what I mean? Is those modes here are not trapped by the presence of the skyrmion. There's no potential term that the magnons feel. It's only because they are hybridized.
Yeah.
So if you make the lattice larger, you're going to keep seeing like the lattice, at least what we take from the diagonalizing the magnon Hamiltonian. Now here, which is like the dynamical, yes, probably.
Okay.
I think you're going to see it. So
Okay.
we check different lattice sizes. You just keep seeing this periodic pattern emerging. And
Okay. Okay. Thanks.
but what is your intuition on that?
Well, I mean, if I have a standing wave, if I put some energy into a liquid or something, it creates a standing wave. If I have boundaries, it creates standing waves.
Mm-hmm.
Or if I have a finite system, even if it's periodic, it creates standing waves. But if it's an infinite system, then I would just get spherical waves that propagate away to infinity. So I would have thought that this would turn into something where you're just sending information out into the
Yes,
into
but
the
because I've
boundaries of the
studied that
system.
problem where you like activate the gyrotropic mode and you radiate
Yeah.
magnons
Yeah.
through, that's not it.
Okay.
That is not it.
Okay.
You might have some radiating magnons. First of all, this is the x direction. Yeah, if you study the z direction, you see there are some magnons radiating and traveling, as you
Okay.
said. But that's not it. That's not the same effect.
Okay.
So there are no emission of magnons.
Okay.
It's yeah.
Yeah, I mean, the skyrmion lives everywhere, so it can do something everywhere. I guess that's what we're seeing.
You mean because we impose periodic, is going to be another skyrmion?
Well, that's true too.
Yeah.
Okay, thanks.
Yeah.
Related question, so what controls the periodicity?
So the wavelength of the extended states that are superimposed. The wavelength of the extended states, the traveling states that are superimposed. So we have these normal modes that live here. This is the dispersion relation of the extended states, like the scattering states. And then there are 6 of them in this example that correspond to translations in the 6th direction of the hexagonal lattice. All of them they're degenerate, so they live at the same energy. And then I can take superpositions of those states. And if I do that, even in a ferromagnet, then I'll get a pattern that looks like that. You could do for any system in reality. The problem with the typical ferromagnet or skyrmions in DMI systems is that those states are down here at k equals 0. So the wavelength of those states is infinite. However, here it's a finite wavelength, and we found it to be comparable to the skyrmion size. In any case, yeah, simple superposition gives you this lattice. And what the skyrmion does is that since it has a mode that can be magnetically activated at the same frequency, and this mode is hybridized by these extended states, you can also activate it dynamically. So if I start from a ferromagnet, I will not see these patterns here, right? Because they are not magnetically active. They only become when they are hybridized by the gyrotropic mode. That's our interpretation so far. But so also here, they're completely absent if I get a DMI system. The same mode, there's no like dynamical pattern or anything like that that has been observed in a simple DMI. Okay, now we could go like to change a bit the wavelength. So we can just check the second mode that I mentioned here that exists at this frequency. So the wavelength is different, and then I'm gonna, we can tune the periodicity of the superlattice. So you see here, the periodicity is different, the same on the localization of the magnon wave function, and also dynamically, the lattice that is generated has a different periodicity. We can even go to the third mode that has exists at k equals 0. That's the mode that has the strongest magnetic dipole. And here we get patterns that are not like this periodic. They are different, both in in-plane component of magnetization and the wave function, and of something similar can be generated also by in-plane fields. So like the properties of this superlattice can be modified by just choosing a different frequency, right? So it's just of course, we would need to do a statistical analysis of all these modes, and that's what we also plan to do, right? Because we have plenty of them that exist at different frequencies, but we were focusing on the low-lying ones for a start. Okay, right. So there's another effect where now helicity becomes important. Is that kind of give rise to nonlinear dynamics. Now, if we focus to the breathing mode, what we find for this system is that the breathing mode really couples strongly to the skyrmion helicity. So that means as the skyrmion breathes, the helicity, as you can see here, this is a time evolution. For the magnetic state we obtained by diagonalizing our Hamiltonian, in the real in the time representation. So as the skyrmion breathes, the skyrmion helicity changes. And here is a plot how the skyrmion helicity changes over time. And this has been plotted using the coherent state representation. So giving a different choice of the total number of magnons, the helicity changes or fluctuates strongly, so depends strongly on the choice of the number of magnons for this mode. So something similar has been observed if we now study the skyrmion dynamics under an AC field. So here you see like the skyrmion helicity under an out-of-plane now AC field also affects the skyrmion helicity, which rotates again, as you can see here, and also depends on the strength of the AC field. Yeah.
I have two questions. The first one is, are those skyrmions fixed on the lattice, or they can move around? And the second one is, if you have a skyrmion in the lattice and you also have a magnons with K different from 0, like a traveling, do they scatter if they encounter the skyrmion in the lattice? So if you have only one skyrmion in a really huge lattice and the magnons are traveling, do they scatter when they bump into the skyrmion? And if so, do they conserve momentum or any other things?
So the skyrmions that we study here are, we allow them to move, so we don't impose them to be pinned, but we don't act on them with some driving force. So in none of these examples we can push skyrmions with the external fields that we're using. In principle, yes, you could do it. On this note, there is some interesting previous work where the skyrmion helicity couples to the moving skyrmion. Okay, if you're interested in that. The second is we also to see magnons are scattered from skyrmions. Like you can send magnons on a static skyrmion, and you can push them around with that. And there's also the back action of those magnons from the presence of skyrmion. But to do that, you have to generate a magnon package or some from at the edge of your material and send it. That's also not what we're doing here. But there is some extensive work on this. So skyrmion really fluctuates over time by the presence of AC fields. And now I'm moving on to what's going on skyrmion lattices. So far, I concentrated on magnons around isolated skyrmions, but the ground state, if we change the magnetic field and the anisotropy, could be a skyrmion lattice, like the one you can see here. I didn't mention that the model also supports skyrmions and anti-skyrmions at the same energy. So we could have like a very large number of metastable states that are, skyrmions at points and anti-skyrmion in some other points. For example, it has been pointed out that such a metastable state where we have skyrmions and anti-skyrmions in this lattice form can exist at higher energies. And in reality, as a note, the only experiments for those materials are based on the topological Hall effect. So you get a large signal from the topological Hall effect of in electron transport, but that large signal doesn't differentiate or doesn't distinguish from all this large number of metastable states. So that's as a side note. But we are focusing on this skyrmion lattice, which is the ground state. It could be anti-skyrmion lattice, but we neglect it for because we found that it gives rise to similar effects. So what would we know now for magnon modes around skyrmion lattices? We have a number of bands in DMI systems. So the low-lying mode at the gamma point corresponds to the translations. So here almost goes to 0. Then we have a number of bands. Most of them correspond to skyrmion deformation, like the one you can see here. And the most important part that I would like to point out is that they are flat bands. So the skyrmions, if they are small enough, they're well separated, and the motion of this localized mode doesn't have any dispersion. So effectively, the skyrmions in this lattice, they don't interact with each other. Now we repeated this calculation for a skyrmion lattice like the one you see here in a frustrated system. Again, we found a number of modes. On top of the translational, we found a band that corresponds to helicity. Again, so we have 2 modes because we have 2 symmetries, translation and rotation, that vanish at the gamma point, and also a large number of all these modes. And the most important fact, in comparison to the DMI systems, is that almost never we get a flat band. And that's because even the skyrmions are very small, could be isolated from each other. If you remember what I said before, there's also this skyrmion tail, and that leads to strong skyrmion interactions even at large distances. Yeah.
Quick question regarding the skyrmion lattice. So, like in your previous slide, you were showing or 2 slides ago, you were showing so this is like in a skyrmion, there is periodic boundary condition. So in principle, there is already like a skyrmion lattice here, just because it's periodic boundary conditions. So what's the difference between this system with periodic boundary conditions compared to the skyrmion lattice like plot you were just showing?
There is no so here effectively you have an isolated skyrmion. So we diagonalize the problem. So periodic is here for the dynamics, but here we diagonalize the problem in real space. You don't have real periodicity in the K space.
No, I was referring to the periodicity in real space.
So we diagonalize a finite Hamiltonian. We don't take boundary effects, but this is diagonalized in the real space and refers to an isolated skyrmion.
So there is no periodic boundary conditions here.
I don't understand the question because the ground state here. So you focus on the unit cell, so that contains only a skyrmion.
Yeah. So this I think goes back to Bill's question. So if you go one slide,
After?
Before, sorry. Yeah, so when we were discussing this, there was this question about the periodicity and whether the skyrmion is interacting with other skyrmion and that kind of stuff. So I understand that here there is periodic boundary conditions being used to determine. So as a consequence, this is already a lattice of skyrmion. But the only band that you got was this Mexican hat-like band. Now you're presenting like some results where we really can see the lattice of skyrmions, and then there's like the appearance of like multi-bands. So I'm just like trying to connect what was done, what have you done from going from this part to the skyrmion lattice per se.
So I'm not really sure what you don't understand, but the skyrmion lattice, so the ground state is like a structure that has this periodicity, and then we go from real space to momentum space. We use the periodicity of the skyrmion lattice. So, okay? That's not the same like we do here. So the band structure there would mean that, let's say the simple example here, at the gamma point, all the skyrmions are translated together, but away from the gamma point, that's why it costs an energy. They're not translated together, so there is like a K modulation over. I don't have a good plot here, but there's a K modulation on these localized modes. So for the breathing mode, all will, at the gamma point, all of them move together. Away from the gamma point, some are here, but some are at a different phase of this breathing. Okay. So this is like, I was saying that the bands here are highly dispersive, and that is because corresponds to excitations of skyrmions that almost always interact, and they interact because we have those small fluctuations of the skyrmion tail, such that the skyrmions, even if they are farther away, they do feel each other. So I'll get back into that very soon. But what we know also for DMI systems is that these bands are topological. So if we take the bands of a DMI system, we can appoint to each of those bands a chair number, which is calculated for magnetic systems according to this formula, which you can find here. And as an immediate consequence, if we have a finite system, so if we have edges, then if we look like what happens above a band with non-trivial chair number, then we have the emergence of chiral edge states that exist here in the gap. As it has been like beautifully shown by Sebastian Diaz and his collaborators for skyrmions in ferromagnetic DMI lattices and antiferromagnetic skyrmion lattices. So that's like another aspect that we would like to explore. So we defined the chair numbers for the bands that we found, and we reported here. There is some band touching where we were not sure. We still have to work because there is one has to be very careful when the curvatures of the two bands touch each other. But surprisingly, we found that the helicity band has a high topological charge. Translations similar to the DMI case is 0, and so on. So that's like a very interesting avenue to explore a bit better. So I didn't mention, I forget to put the citation here, that here is like the strength of the magnetic dipole. One could look for electric dipoles. So we know that some of these bands couple to magnetic fields, but some others are going to couple to electric fields. So especially when one studies skyrmion lattices in cavities. They're going to couple both to the magnetic field of the cavity and the electric field of the cavity. So for a given material, it's also worth, and we plan to explore a bit, what's the electric dipole of those bands. And I'm very close to the end. What I would like also to study is how like the distance of the two skyrmions affects the dynamics of the helicity. And so we found something very interesting. So first of all, the fact that this skyrmion has some tails is gonna give rise to those fluctuations between the energy of the two skyrmions as a function of their relative distance. So here, this Q is imaginary and has like the fact that it decays exponentially, but the imaginary part of this number here corresponds to those fluctuations, and also depends on the relative helicity of the two skyrmions. And this has also been reported before, this like fluctuating. So that means that it goes from positive to energy, depending on the relative distance. The skyrmion interaction can change from attractive to repulsive, contrary to what Bill told us some days ago. But indeed, for skyrmions in DMI systems, this is going to drop. But here we have these interesting fluctuations. And that's what we explore. So what is the cost of energy to excite the skyrmion helicity, depending on the distance of the two skyrmions? So if they have a fixed distance, for example, I think here it's 12 in this example, then the two skyrmions start initially with the same helicity. That's going to minimize the energy here, and then as a function of time, they will rotate on an opposite direction. So the one goes like that, and the other goes like that. Over a period, they're going to meet again. But if we put them further away, they minimize their energy and they have opposite helicities. So the relative helicities here is opposite, pi over 2, I think. Dynamically, the one will rotate with the same direction. So they're going to meet, but then they're going to have a different helicity. So it's kind of interesting, like what would be an interesting direction to go from here. So the fact that where we place the skyrmion depends strongly on like the level or the type of attraction, but also on the relative helicities of those two skyrmions. So that's like something we found and I reported, and I would be interested in exploring it further. So that brings me to the end of this talk. I wanted to kind of point out that skyrmions in frustrated systems, since we have this helicity, which is highly tunable, can offer many exciting new things. One would be whether we can encode information in the quantum level, and also like other features that frustration has to offer in terms of those dynamical magnon lattices that I mentioned before. So thank you for your attention.
Thank you very much, Christina. Sylvia.
Question about the coupling to the electric. So where does the electric dipole come from? And I did not understand the.
So the textures in frustrated systems give rise to have a dipole coming from the spin current mechanism. This we know already. So then they're going to couple to the electric field. And we also know, I didn't report it, but it has been shown that you can control skyrmion helicity, for example, using electric field. So they have a polarization that couples to the electric field, the texture itself.
Okay, but that means that there is some charge displaced. So where is the charge?
So it's effectively, there is the electrons, right? But effectively you have a polarization in terms of the magnetization. And yeah, I don't remember, but I think it's like, here might be crows.
Green in green is very bad.
Okay. So it's just the outer product of neighboring spins. Between, that's like...
Okay, but at the end, so it's
the
some kind
dipole.
of perturbative
Yes.
in spin orbit or something.
Yes,
and
exactly. And then depends on
Okay.
the crystal symmetry and everything. But in a classical level, there is a polarization on those materials, and it couples to the electric field, and it's gonna couple to the bands as well.
Thank you.
Yeah.
More questions? We already had plenty. So let's
Thank
thank
you.
the speaker again.
Thank you.
So now we have Jean presenting.